Welcome to AP Chemistry Review and Practice. My name is Michael Faribaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. This episode is part 2 of a 2-part lesson. I have written a practice exam, multiple choice section. Now, this is not an official practice exam from the College Board. My practice exam contains 60 multiple choice questions, and these are questions that I wrote which are intended to be similar with respect to the format, difficulty level, and content to the types of multiple choice questions that students would see on the AP Chemistry exam. But if you're watching this video, but you have not yet watched episode 32, then you should begin your review of my practice exam by watching episode 32. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Check out the links in the video description area, which include the link to my practice exam multiple choice section. Now again, if you're watching this video, but you have not yet downloaded my practice exam, and you have not yet watched episode 32, go back to episode 32 where I gave information and instructions for taking my practice exam. So in episode 32, you can check your answers and hear my explanations and strategies for answering questions 1 through 30 of my practice exam. Now, if you've done that and you're ready to check your answers to questions 31 through 60, continue watching this video. Okay, let's get started. This is question 31. In question 31, we are given a chemical equation, and it says at 298 Kelvin, the reaction shown above has a delta H of negative 176 kilojoules per mole of reaction, and a delta S of negative 285 joules per Kelvin mole of reaction. The reaction is run at both 298 Kelvin and 698 Kelvin. Which of the following correctly identifies the thermodynamic favorability for the reaction at the two temperatures? Assume that delta H and delta S do not change with temperature. So we're going to use the Gibbs free energy equation, which is delta G equals delta H minus T delta S. And so we have everything we need to calculate the value of delta G at both 298 Kelvin and 698 Kelvin. So I will begin with 298 Kelvin. There's my delta H, negative 176 kilojoules per mole of reaction. My temperature is 298 Kelvin. Now, watch out. The delta S is negative 285. But look at those units. Those units are actually joules, not kilojoules. So you need to divide by 1,000 to convert from joules to kilojoules. So the delta S with the proper units is actually negative 0.285 kilojoules per Kelvin mole of reaction. Now, when I pick up my calculator, it's going to be negative 176 minus the product of 298 and negative 0.285. And so when I do that math, I get a delta G at 298 Kelvin that is negative 91.1, and the units are kilojoules per mole of reaction. Now, what does the negative delta G tell us about the thermodynamic favorability? Well, if the delta G is negative, then the reaction is thermodynamically favored at that temperature. So if it's favorable at 298 Kelvin, we know that the correct answer is either C or D, because in choices A and B, it says it's unfavorable at 298 Kelvin. So we can eliminate choices A and B. Now let's repeat the process, but this time I will plug in a temperature of 698 Kelvin. And when I do that math, what I discover is that it turns out to be a positive delta G at 698 Kelvin, which means that now it is unfavorable at 698 Kelvin. So I can eliminate choice D. Now, this happens sometimes when you're analyzing the delta H and the delta S. So if both delta H and delta S are negative, then the reaction might be favored at low temperatures, but then unfavorable at high temperatures. And that's what we see here. So the correct answer to question 31 is choice C, favorable at 298 Kelvin, but unfavorable at 698 Kelvin. In question 32, we are given the description of an experiment. It says, a chemist determined the concentration of a potassium sulfate solution by adding 1 molar barium nitrate solution until no more barium sulfate precipitate is formed. Now, the precipitate was filtered out of the solution and then dried and weighed. The chemist used the mass of the precipitate to determine the concentration of the potassium sulfate solution. Which of the following descriptions of the calculated concentration of potassium sulfate is matched correctly with a laboratory situation that would explain that particular result? So this is common on the AP Chemistry exam, either in the multiple choice section or the free response section, where they ask you to describe how a certain laboratory situation will affect the results of an experiment. Now, before I analyze each of the 4 laboratory situations in this question, let me give you a brief overview of this experiment. So we have a potassium sulfate solution, but we don't know the concentration. We add an excess amount of the barium nitrate, and the purpose of adding the barium nitrate is to convert all of the sulfate ions that were present in that solution into a precipitate of barium sulfate. But now we have to remove that solid barium sulfate from the solution, so the precipitate was filtered. And so now we have a barium sulfate sample that has been filtered and dried and weighed. And if we know the grams of barium sulfate, we can convert from grams to moles. And based on the 1-to-1 mole ratio, then if we know the moles of barium sulfate, then we also know the moles of the potassium sulfate. And if the purpose of the experiment is to calculate the concentration, we just take the moles of the potassium sulfate, we divide by the volume, and we get the molarity. So now as we consider the 4 laboratory situations in question 32, we can consider whether that laboratory situation would explain why the calculated concentration of potassium sulfate is either less than or greater than the actual concentration. Let's go ahead and start with choice A. In choice A, it says that the solid barium sulfate was not completely dried before being weighed. So what would that do to the mass of the solid barium sulfate? Well, if it's not completely dry, then the mass of barium sulfate would be too high. How will this affect our results? Well, now your calculated value for the moles of barium sulfate and the moles of potassium sulfate would be too high, and your calculated value for the concentration of potassium sulfate is too high. But what did they say in choice A? It said the calculated concentration of potassium sulfate is less. So we can go ahead and eliminate choice A. Now on to choice B. This laboratory situation is that the filter paper had a hole in it and some of the solid barium sulfate precipitate washed through the filter paper. So now we actually have less barium sulfate than we should. And if your mass is too low, your calculated value of moles is too low. So your calculated value for the concentration of potassium sulfate would be too low, and that's what they say in choice B. So we know at this point that choice B is the correct answer, but let me convince you why choices C and D are incorrect. So here's the laboratory situation in choice C. Now the chemist accidentally used a solution of 2 molar barium nitrate instead of 1 molar. But remember that the purpose of the barium nitrate is to add it in an excess amount. Since an excess amount of barium nitrate was added, then if you use a solution of barium nitrate with an even higher concentration, then this does not affect the results. So we can eliminate choice C, and then finally, choice D, the laboratory situation is similar to choice B. It says a small amount of solid barium sulfate fell off the filter paper onto the floor. before measuring the mass of the filter paper and precipitate. So just like in choice B, if your mass of the solid barium sulfate is too low, then your calculated value for the concentration of potassium sulfate would be less. And so because it says greater in choice D, we can go ahead and eliminate choice D. So again, the correct answer to question 32 is choice B. If the filter paper had a hole in it, then that would cause your mass and your calculated value of moles to be less than what it should be. All right, let's go ahead and take a look at question 33. Question 33 relates to Unit 5, Kinetics. It says, a scientist performed 2 trials in a study of the decomposition reaction of N2O5, represented by the equation shown above. The decomposition reaction is first order with respect to N2O5. Based on the data in the table above, which of the following provides the correct prediction for the values of the initial rate and the rate constant for trial 2? So as you can see in the 4 answer choices, we're not actually doing any math to calculate the value of the rate constant or the rate. We are simply comparing the initial rate and the rate constant in trial 1, which are represented as R1 and K1, with the initial rate and the rate constant in trial 2. Now they tell us the decomposition reaction is first order with respect to N2O5. So what I will do is write the first order rate law. Rate equals the rate constant K times the concentration of N2O5. Now in trial 1, we have a 0.10 molar initial concentration. So I've got R1 for the initial rate, and I've got K1 for the rate constant, and this is all for trial 1. So what happened in trial 2 is they doubled the concentration, the initial concentration of N2O5. So what I have to determine is, will the rate in trial 2 be the same or doubled? And will the rate constant in trial 2 be the same or doubled? Now in topic 5.2, Introduction to Rate Law, it says that the rate constant is temperature dependent. So what does that mean? It means that if you change the temperature, then you can change the value of the rate constant. But that's not what happened in this experiment. So because the temperature is the same in each trial, then we know that the rate constant K should also remain the same. So now I can go ahead and eliminate choices B and D because they say that the rate constant is doubled, and that's incorrect. Well, something has to be doubled as you go from 0.1 molar to 0.2 molar. So what happened is that the initial rate in trial 2 is twice as much as the initial rate in trial 1 because they doubled the initial concentration of N2O5, and that is a first order rate law. So the correct answer to question 33 is choice C. The initial rate in trial 2 would be doubled, but the rate constant stays the same. Moving on to question 34, this is a stoichiometry question involving a limiting reactant. It says, chromium metal reacts with oxygen gas in a sealed container to produce solid chromium-3 oxide, and they give us the molar mass, according to the equation shown above. The initial masses of the reactants are listed below. So I have 52 grams of chromium, and that represents 1 mole of chromium. I have 32 grams of O2, and that also represents 1 mole of O2. Assuming that the reaction goes to completion, which of the following identifies the limiting reactant and the maximum amount of this chromium-3 oxide that could be produced? So if I have 1 mole of chromium, based on the information in the balanced chemical equation, there's 2 moles of chromium-3 oxide produced for every 4 moles of chromium that reacts. And there's 152 grams of chromium-3 oxide for every 1 mole. So if I do 2 divided by 4 times 152, I get 76 grams of chromium-3 oxide produced. Let's go ahead and check. If I have 1 mole of oxygen, well, now my ratio based on the coefficients would be 2 moles of chromium-3 oxide produced for every 3 moles of oxygen gas. And therefore, when I do that math of 2 divided by 3 times 152, I get 101 grams. Now what I'm looking for is the identity of the limiting reactant, so I will choose chromium because it produces a smaller amount of the product, and now the maximum amount of chromium-3 oxide that could be produced is 76 grams. That's my theoretical yield. So the correct answer to question 34 is choice A. In question 35, we can see two Lewis diagrams. It says two different Lewis diagrams are shown above to represent the thiocyanate ion, which has the chemical formula SCN-. Which of the following indicates the preferred representation for the bonding in the thiocyanate ion and best explains why? Now I can see, looking at the four answer choices, that choice A and choice C involve something known as formal charge. Let me review how I teach formal charge. So the formal charge is equal to the valence electrons for that particular atom minus the sum of the dots and the bonds. And if we can draw at least two different Lewis structures for a molecule or a polyatomic ion, then we can use formal charge to determine which Lewis structure is more dominant or preferred. So here are the guidelines. The dominant Lewis structure is usually the one in which the atoms have formal charges that are closest to zero. And if the Lewis structure contains a negative formal charge, the dominant Lewis structure is the one in which the negative formal charge is assigned to the more electronegative atom. All right, I will begin with valence electrons minus the sum of the dots and the bonds. So starting with structure 1, for that nitrogen, it's going to be 5 minus 6, so -1. For the carbon, it's going to be 4 minus 4, so 0. And then for the sulfur, it's going to be 6 minus 6, also 0. Now, it's impossible to get all three atoms to have a formal charge of 0 because we can see that this polyatomic ion has an overall charge of -1. So the best we can do is to get those formal charges as closest to 0 as possible, and that would be 0, 0, and -1, so that the sum of the formal charges would equal the overall charge on this polyatomic ion. So it's looking pretty good right now for structure 1. Let's move on to structure 2. Okay, nitrogen, 5 minus 7. Ooh, -2. I'm already not crazy about structure 2 because I'm trying to get those formal charges to have the smallest magnitude possible, closest to 0. Now, the carbon happens to be 4 minus 4, that's 0. And then the sulfur would be 6 minus 5, so +1. So it looks like structure 1 is preferred to get the magnitude of the formal charges as closest to 0 as possible. So based on my analysis of the formal charges in structure 1 and structure 2, structure 1 is preferred. The formal charges are closer to 0, and the negative charge happens to be on nitrogen, which is the most electronegative atom. So looking at our four answer choices, choice B says structure 1, but the justification is incorrect. It says because it has two double bonds and is therefore more symmetrical. That's not the reason why. And it's definitely not structure 2. The -2 is not as good as the -1. We're trying to get the magnitude of the formal charges to be as closest to 0 as possible. So I will eliminate choices C and D. The correct answer to question 35 is choice A, structure 1, because it places a formal charge of -1 on the element that has the highest electronegativity value, and then also the formal charges are closer to 0. Question 36 involves a chromatography experiment. It says, the structural formulas of benzene and phenol are shown above. A chemist sets up a column chromatography experiment to separate a mixture of these two substances. The column is filled with a polar stationary phase, and a non-polar solvent is poured through the column. Which of the following correctly identifies the substance that should pass through the column at a faster rate and provides the correct justification? Now, with many chromatography questions, the polarity of the substances in the mixture is relevant to understanding why one substance moves a farther distance than another substance. And this is true whether it's paper chromatography or, in this case, column chromatography. So let's consider the polarity of benzene and phenol. Which substance appears to be very symmetrical in which all of the bond dipoles would cancel out? Well, that's going to be benzene. Symmetrical, all the dipoles cancel out, so benzene is non-polar. But on the other hand, we have phenol with that OH group that is asymmetrical. The dipoles do not cancel out, so benzene is non-polar and phenol is polar. Now, we have our non-polar solvent that is poured through the column, so the mobile phase is non-polar. A mixture of benzene, which is non-polar, and phenol, which is polar, is added to the top of the chromatography column. And now the components of this mixture travel through the column at different rates. So the solvent is the mobile phase because it flows and moves through the column, and the substance that is more attracted to the mobile phase should pass through this column at a faster rate. So which substance, benzene or phenol, is more attracted to the non-polar solvent? Considering that a non-polar substance should be more attracted to the non-polar solvent, benzene is non-polar and should pass through the column at a faster rate because it is more attracted to the non-polar mobile phase. So we know that the correct answer to question 36 is benzene. I will go ahead and eliminate choices B and D. And the reason why benzene should pass through the column at a faster rate is because molecules of benzene are more attracted to that mobile phase, the non-polar solvent, than to the stationary phase. So again, correct answer to question 36 is choice A. In question 37, it says the structural formulas of two compounds that are liquids at room temperature are shown above. Which of the following statements best explains the observation that compound 1 boils at 70 degrees Celsius, whereas compound 2 boils at 97 degrees Celsius? So clearly what we have to do to answer question 37 is account for the higher boiling point of compound 2, which is going to be related to stronger attractive forces between the molecules. So I'm going to go ahead and get rid of or eliminate choice D because it says the covalent bonds present in compound 2 are stronger than those in compound 1. So it's not about the covalent bonds within the molecule, it's about the attractive forces between the molecules. Now, are these two substances, are they both polar, both nonpolar, or one of each? Well, considering that we have a certain level of asymmetry in each structure, I don't think the bond dipoles in either of these molecules will cancel out. They don't look very symmetrical, so both of these molecules are classified as polar. That means that each of them experiences a combination of London dispersion forces and dipole-dipole forces. Now, looking at the four answer choices, we already eliminated choice D because of the covalent bonds. I'm going to eliminate choice A because it says that compound 2 experiences dipole-dipole attractive forces, but compound 1 does not. And in fact, they both experience a combination of London dispersion forces and dipole-dipole forces. So now I'm down to choice B and C. So what about the hydrogen bonding attractive forces? Remember that for a molecule to experience hydrogen bonding attractions with other molecules, then the hydrogen needs to be directly bonded to either nitrogen, oxygen, or fluorine. And we do see that feature in compound 2. There is a hydrogen directly bonded to an atom of oxygen, so compound 2 also experiences hydrogen bonding attractive forces. So it looks like the correct answer to question 37 is choice B. But some of you watching this video might wonder, why is choice C incorrect? It says the London dispersion forces present in compound 2 are stronger than those in compound 1. Well, with London dispersion forces and the polarizability of molecules, that increases with an increasing number of electrons and the size of the electron cloud. Let's focus our attention on oxygen versus bromine. Now, oxygen has 8 electrons, whereas bromine has 35 electrons. So it turns out that bromine has a larger electron cloud than oxygen. So saying that the London dispersion forces present in compound 2 are stronger, that part is actually incorrect. So the correct answer to question 37 is choice B. Compound 2 experiences hydrogen bonding attractive forces, but compound 1 does not. In question 38, it says the complete photoelectron spectrum of beryllium is represented above. Which of the following correctly identifies the atomic orbital represented by peak X and provides a valid justification? So the correct answer to question 38 is either 1s or 2s. The electron configuration of beryllium is 1s2, 2s2. And so if we look at the binding energy on the x-axis, we can see that peak X has a higher binding energy than peak Y. The higher binding energy means it's more difficult to remove those electrons from the atom. And that means it's going to be a stronger attraction toward the nucleus of the atom. So is it 1s or 2s? Well, the 1s electrons are going to have a higher binding energy because they have a stronger attraction toward the nucleus and are more difficult to remove, whereas the electrons located in the 2s are farther away from the nucleus, and so they have a weaker attraction toward the nucleus, and they are easier to remove. So closer to the nucleus is going to be part of our argument in terms of a stronger attraction toward the nucleus. I'm going to go ahead and eliminate choices C and D because we know it's 1s. Now in choice B, it says 1s, but it says because the electrons in the 1s orbital experience greater electron-electron repulsions. So it's attractive forces toward the nucleus that would explain why the 1s electrons are more difficult to remove. Electron-electron repulsions is not a consistent justification. That would actually imply it's somehow electrons pushing away from each other, but I'm looking for the stronger attraction toward the nucleus to explain that higher binding energy. So the correct answer to question 38 is choice A. In question 39, it says 4 containers each hold a sample of helium gas. Based on the information in the table, which container is at the highest temperature? So looking at the information in the table, I can see that the mass of helium is listed, and I can easily convert from grams to moles. I see the volume of the container, and I see the pressure of the gas. So this would be a good time to use the ideal gas law. PV equals nRT, and I can just rearrange the ideal gas law and calculate the temperature. Now, I'm not going to actually plug in the value of R and calculate the temperature in terms of Kelvin. All I need to do is determine which container is at the highest temperature. So what I will do for each of these 4 choices is I will simply plug in the numbers for volume and pressure and number of moles and see which is the largest value. Now, on the periodic table, we can see that helium has a molar mass of 4 grams per mole. So containers A and C contain 4 grams of helium, or 1 mole, and containers B and D contain 8 grams of helium, which would be 2 moles. All right, starting with choice A. It's going to be PV over NR. That would be pressure times volume, in this case 5 times 5, and then the number of moles is 1. So that would be 25 over R is my expression for choice A. Now I'm going to move on to choice B. Still going to be 5 and 5 on the top for the pressure and the volume, but now I have 2 moles, so that would be 25 divided by 2, or 12.5 over R. Now moving on to choice C, I have a pressure of 4 atmospheres and a volume of 8 liters. That would be 4 times 8, and I have 1 mole, so 4 times 8 is 32. 32 over R, and then finally for choice D, I still have a pressure of 4 atmospheres and a volume of 8 liters, but I have 2 mole. So for choice D, it's going to be 4 times 8 divided by 2. Now looking at the 4 choices, we can see that the largest value is choice C. So choice C would be the container that is at the highest temperature. In question 40, it says lattice enthalpy can be defined as the change in enthalpy, or the delta H, associated with the separation of a solid crystal into gaseous ions, as represented in the table below. So we can see in the table there's sodium chloride and potassium chloride that start out as solids, and then they are broken up into gaseous ions. So that is what lattice enthalpy is describing in that table. And the question asks, which of the following statements about lattice enthalpy is supported by the data listed in the table above? Now, we know from topic 2.2, specifically about Coulomb's law and the attractions between ions, that larger charges lead to stronger attractions between the ions. We also know that smaller ions, in other words, a smaller distance between the ions, lead to stronger attractions between the ions. And so what I like about question 40 is it's a good example of the advice that I normally give you at the end of each lesson in AP Chemistry Review and Practice. And that piece of advice is read the question carefully and make sure you are answering the question that is being asked. Look at choice C. it says that lattice enthalpy, it increases with the increasing charge of the ions in the compound. Now, that's true, but it's not supported by the data listed in the table above. So look at the charges. We see sodium is +1, potassium is +1, chloride is -1. We don't have any evidence in the table that shows examples of compounds with ions with different charges. So although choice C is a true statement, it's not supported by the data in the table above. So we have to eliminate choices A and C, which talk about the charges of the ions, because we don't see any difference between the charges on the ions. Sodium chloride and potassium chloride, they're both +1 and -1. So now, what is the correct answer to question 40? So it is also true that smaller ion sizes result in stronger Coulombic attractions between the ions. And as you already know from the periodic trend that atomic radius increases as you go from top to bottom down a group, that makes the sodium ion smaller in size than the potassium ion. So is the lattice enthalpy of sodium chloride higher than the lattice enthalpy of potassium chloride? Yes. And so what does that tell us? It takes more energy to separate the sodium chloride compound because the ion sodium is smaller and there's a stronger lattice energy because of that stronger Coulombic attraction. So the correct answer to question 40 is choice B. Lattice enthalpy increases with the decreasing radii of the ions in the compound, and that data is supported by the examples that are listed in the table above. In question 41, it says, which of the following samples contains the greatest percentage of nitrogen by mass? So we see 4 particle diagrams. All we have to do to answer question 41 is count the particles and do the math. So on the periodic table, nitrogen has a mass of 14, oxygen has a mass of 16, and hydrogen has a mass of 1. Let's begin with choice A. So I will count the particles of nitrogen, oxygen, and hydrogen and determine the total mass of this mixture. So I see 4 atoms of nitrogen, I see 4 atoms of oxygen, and I see a total of 6 atoms of hydrogen. Again, these numbers for the masses from the periodic table are 14, 16, and 1. So it's going to be 4 times 14, 4 times 16, 6 times 1, and that gives me a total mass of 126. Now, the mass of nitrogen in that mixture is 56. So what I'm doing on my calculator is 56, the mass of nitrogen, divided by 126, the total mass of the mixture. And when I do that math, I get a percentage of nitrogen by mass of 44%. All right, well, that's 1 down, 3 to go. So same process for choices B, C, and D. So on to choice B. Now, I also see 4 atoms of nitrogen. I see 4 atoms of oxygen, but this time I have only 4 atoms of hydrogen. So my total mass will be slightly less than 126. So 4 times 14, 4 times 16, and then 4 times 1. So now since my total mass is 124, but I still have 56 for the nitrogen, my prediction is that I will get a slightly higher percentage of nitrogen by mass. And when I do that math of 56 divided by 124 times 100, I get 45% nitrogen by mass. All right, 2 down, 2 to go, but we know it's definitely not choice A because we're looking for the greatest percentage of nitrogen by mass. On to choice C. Now I see 6 atoms of nitrogen, I see 2 atoms of oxygen, and I see 6 atoms of hydrogen. So 6 times 14, 2 times 16, 6 times 1, and that is a grand total of 122. So the mass of nitrogen is 84 in that mixture. So 84 divided by 122 times 100. I have 69% nitrogen by mass, so I can eliminate choice B. Now let's go ahead and see if choice D has an even higher percentage of nitrogen by mass. I still see 6 atoms of nitrogen, but I only see 1 atom of oxygen, and I see a total of 8 atoms of hydrogen. So 6 times 14, 1 times 16, 8 times 1. Now, the grand total in terms of the mass of the mixture is 108. So it's going to be 84 divided by 108 times 100. So we have now determined that the correct answer to question 41 is choice D, with 78% nitrogen by mass in that mixture. That's why choice D is the correct answer. In question 42, it says it is proposed that the formation of C2H5Cl proceeds via the following two-step reaction mechanism. So I can see step 1 and step 2, and it says that the energy profile for this reaction is shown below. So I can see an activation energy for step 1, and I can see an activation energy for step 2. Now, the higher the activation energy is, the slower the reaction rate is. So this is the activation energy for step 1, which is larger, and this is the activation energy for step 2, which is smaller. So now we know that step 1 is the slow rate determining step, and step 2 is a fast step in this mechanism. Now, one more thing to consider, the overall reaction is either classified as endothermic or exothermic. Let's compare the energy of the reactants with the energy of the products, and then we can decide if this is endothermic or exothermic. So this overall reaction is exothermic because the potential energy of the products is less than the potential energy of the reactants, so that means that energy is released for this overall reaction. Now, we have enough information to answer question 42. It says, based on the energy profile, which of the following identifies the rate determining step of the mechanism, so that's step 1, and correctly describes the energy change for the overall reaction, which is exothermic. So the correct answer to question 42 is choice B. In question 43, it says, which of the following equations represents a process for which the value of delta S, the change in entropy, is closest to 0? So what I will do as I analyze these four choices is I will count the number of moles and I will consider any phases of matter. Looks like the majority of these substances are in the gaseous state, but let me go ahead and count the number of moles on the left and the right. So starting with choice A, 2 moles of gas are changing into 3 moles of gas, so entropy should be increasing. In choice B, we have 1 mole of liquid changing into 1 mole of gas. Again, I would say that entropy is increasing. And now we come to choice C. So when I consider choice C, I see 3 moles of gas on the left, and I also see 3 moles of gas on the right. So therefore, the entropy change for choice C should be small and close to 0. And then finally, looking at choice D, I see a total of 6 moles of gas on the left, and I see a total of 7 moles of gas on the right, so that would involve an increase in entropy. So the correct answer to question 43 is choice C. Because there's the same number of moles of gas on each side of the equation, we would expect the value of the change in entropy, or delta S, to be closest to 0. In question 44, it says, based on the reaction and data tables shown, what is the value of the enthalpy of formation for CCl4, carbon tetrachloride? Now you can look at the data table and you can see that carbon tetrachloride has a question mark next to it. So that tells us this is the enthalpy of formation that we don't know. But we know everything else, including the change in enthalpy for the overall reaction. So our equation involving enthalpy of formation is the following. The enthalpy change for the reaction is equal to the sum of all of the enthalpy of formation for the products minus the sum of all of the enthalpy of formation for the reactants. And we know that the delta H for this reaction is negative 106 kilojoules per mole of reaction, so I will put negative 106 on the left side of that equation. Now, focusing on CF4, which is one of the products, that value in the table is negative 933 kilojoules per mole, so I will add that to the setup for my calculation. And the other reactant that I see is HCl. Now, be careful. Watch out for this mistake, because in the table it says that the delta H of formation for HCl is negative 92, but there is a coefficient of 4 in the balanced chemical equation. So don't forget to use the coefficients when you set up your calculation involving this enthalpy of formation and products minus reactants. All right, we are done with all of the products. Now I will focus on the reactants. So I have HF as one of the reactants, and that value is negative 273. Again, don't forget there's a coefficient, so it's going to be 4 times negative 273, and that's a reactant. Now the other reactant is CCl4, but since I don't know that value, I will just put that in as X. Okay, I have the correct setup for my calculation, but I still have to calculate the value of the enthalpy of formation for CCl4. So be careful not to make any careless errors, mathematical errors, errors with sign. So watch out for that. So the next thing I will do is simplify some of the numbers that I have. So I still have negative 106 on the left. And when I combined all of the products, I got negative 1,301. And as far as the 4 times negative 273, I got negative 1,092. Again, watch out for negative signs. So the next thing I will do is negative 106 is equal to negative 209, when I did that math, minus X. Now, the correct answer for the enthalpy of formation for CCl4, it works out to be negative 103. So look at choice C. If you made a careless error with the sign, you might pick choice C, but choice B is the correct answer. And remember, I told you to be careful about the coefficients. Choices A and D are incorrect, but they are based on the student who forgot to use the coefficients in the setup for their calculation. Again, the correct answer to question 44 is choice B. In question 45, it says, information about 2 buffer solutions are represented in the table below. After measuring the initial pH of each buffer, a sample of 0.050 mole of solid sodium hydroxide is added to each buffer. Each solution is stirred until the sodium hydroxide dissolves completely. Assume that the volume of each solution remains constant. So I see buffer X and buffer Y. Each buffer has the same volume, which is 1 liter. Each buffer contains the same components. We have HF, which is hydrofluoric acid, and we have NaF, which is sodium fluoride. But the difference between buffer X and buffer Y is in the concentration of the buffer components. So in buffer X, the concentration is 0.10 molar for each buffer component, whereas in buffer Y, it's actually 1 molar for each buffer component. Now, the initial pH of each buffer is the same. The amount of sodium hydroxide added to each buffer is the same. And what we have to compare is the final pH at the end of the experiment. It says the pH of each buffer is measured at the end of the experiment, but which of the following correctly predicts how the final pH of buffer X should compare to that of buffer Y and provides a valid justification. So looking at the 4 answer choices, it's going to be related to buffer capacity. So that is topic 8.10. And the higher concentration of the buffer components leads to a higher buffer capacity. The higher buffer capacity means it's better able to resist changes in pH when either a strong acid or a strong base is added to the buffer. So, as I mentioned, buffer X has a lower concentration of the buffer components, whereas buffer Y has a higher concentration of the buffer components. So in terms of buffer capacity, buffer X has a smaller buffer capacity with a smaller concentration of the buffer components, and buffer Y has a higher buffer capacity with a higher concentration of the buffer components. The higher the buffer capacity is, the better the buffer is at resisting a change in pH. So we added sodium hydroxide. The same amount of sodium hydroxide was added to each buffer. Now, since sodium hydroxide is a base, we expect the pH to increase. So the final pH should be higher than 3.17. Now, buffer X has a smaller buffer capacity, so its pH should change even more because there are fewer moles of the buffer components available to react with the sodium hydroxide. So looking at the four answer choices, choices B and D are incorrect because the justification says that buffer X has a higher buffer capacity, but that is incorrect. Let's go ahead and eliminate choices B and D. We know the pH is going to increase because sodium hydroxide is added, and we are expecting the pH of buffer X to increase even more. So the correct answer to question 45 is choice C. The final pH of buffer X should be higher than that of buffer Y. And the reason why is because buffer X has a smaller buffer capacity. In question 46, it says, based on the resonance structures shown above, what are the bond orders of the two nitrogen-oxygen bonds? Now, before I examine the details of the resonance structures for the NO2- ion, I'd like to show you a molecule that can be described by resonance structures. Now, this is ozone, which has the chemical formula O3. A single bond has a bond order of 1. A double bond has a bond order of 2. Now, the bond order of the oxygen-oxygen bonds in the molecule ozone is equal to 1.5. Why? Because this value of 1.5 represents an average of a single bond, bond order of 1, and a double bond, bond order of 2. That's exactly the situation that we're looking at in question 46 with this NO2- ion. So the correct answer to question 46, what are the bond orders of the two nitrogen-oxygen bonds? They are the same. They are 1.5 and 1.5. Again, the average of a single bond and a double bond for these two resonance structures. In question 47, it says that hydrogen gas and iodine gas react to form hydrogen iodide according to the equation above. The particle diagram shown below is a representation of the system at a certain time during the reaction. Which of the following is the value of the reaction quotient Q for the system at this time? Assume that each particle represents a partial pressure of 1 atmosphere for that substance. So I will do the reaction quotient as products over reactants. I will use partial pressure of each substance. So in the numerator of this reaction quotient, it's going to be the product. So partial pressure of HI, and that's going to be squared because of that coefficient of 2. And in the denominator, it's going to be the partial pressure of the hydrogen and the partial pressure of the iodine. Well, now that I have the reaction quotient, I will count the particles in the particle diagram, starting with HI. I see 2 particles of HI. That would be a partial pressure of 2 atmospheres. I see 3 particles of hydrogen. That would be a partial pressure of 3 atmospheres. I see 2 particles of iodine. That would be a partial pressure of 2 atmospheres. Now that my numbers are in place, I will go ahead and do the math. So 2 squared is 4. 3 times 2 is 6. So I get 4 divided by 6. So the correct answer to question 47 is choice B, because 4 divided by 6 is equal to 0.67. In question 48, it says, which of the following compounds would be most effective at increasing the pH when added to a sample of water? Now, before I look at the details of these 4 chemical formulas, I'd like to show you topic 8.2. And I'm looking specifically at the examples of these strong acids that you should memorize for the AP Chemistry exam. And those strong acids include HCl, HBr, HI, HClO4, H2SO4, and HNO3. So what I have on this slide are examples of ions that do not affect the pH of an aqueous solution. Now, for my neutral cations, I include group 1 and group 2 cations, such as sodium, potassium, calcium, and strontium. And for my neutral anions, you can see that the 5 ions that are listed in this table, chloride, bromide, iodide, perchlorate, and nitrate, why are they neutral? Because they came from a strong acid. So there's an inverse relationship between the Ka for an acid and the Kb for its conjugate base. So because with strong acids the Ka is so large, that means that the Kb for the conjugate base is very, very small. So these do not behave as bases. They are negligible. They don't affect the pH of the solution. So let's go ahead and look at the details of the 4 chemical formulas in question 48. Now the first chemical formula is sodium perchlorate. But since sodium is a neutral cation and perchlorate is a neutral anion, then we can eliminate choice A because it's neutral. Moving on to choice B, I see potassium, which is neutral, and I see bromide, which is also neutral, so we can eliminate choice B. Now, moving on to choice C, this is ammonium chloride. Although the chloride ion is neutral, since ammonium, which is NH4+, it came from the weak base, which is ammonia, NH3, then that means if ammonia is a weak base, then the ammonium ion is a weak acid. Now, the correct answer to question 48 is not choice C. The ammonium chloride, with the ammonium ion behaving as a weak acid, would actually lower the pH when added to a sample of water. So why is the correct answer to question 48 choice D? Even though sodium is a neutral ion, let's focus our attention on the fluoride. So if hydrofluoric acid, or HF, is a weak acid, that means its conjugate base, the fluoride ion, is a weak base. That's exactly what we're looking for. So for question 48, which of the following compounds would be most effective at increasing the pH when added to a sample of water? That would be sodium fluoride. So here is a net ionic equation in which the fluoride ion can react with water as a weak base, and it produces HF along with the hydroxide ion. So when added to a sample of water, sodium fluoride, because of the presence of the fluoride ion as a weak base, would increase the pH. In question 49, it says, based on the information in the table above, which of the following statements is the most accurate description of what happens when a pure sample of 8.1 grams of gaseous bromine undergoes condensation? This is another example of read the question carefully and make sure you are answering the question that is being asked. The process in the table is bromine changing from a liquid to a gas, and that's the enthalpy of vaporization, that's 31 kilojoules per mole. So even though going from a liquid to a gas, or evaporation, is an endothermic process in which thermal energy is absorbed, the question is talking about condensation. So that's going from a gas to a liquid. And if evaporation is an endothermic process, that means that condensation is an exothermic process. So thermal energy is released when bromine undergoes condensation. Let's go ahead and eliminate choices A and C, which say that thermal energy is absorbed. Now what we have to do is take that 8.1 grams of bromine and do a calculation involving the delta H of vaporization. So I will begin with 8.1 grams of bromine. I will first use the information on the periodic table to go from grams to moles. So 1 mole of bromine has a mass of 159.8 grams. Now, the delta H of vaporization, that is 31 kilojoules per mole. So if I were going from a liquid to a gas, then 31 kilojoules would be absorbed per mole. But if I'm going from a gas to a liquid, then 31 kilojoules would be released per mole. So there's my 31 kilojoules per mole. When I pick up my calculator, it's going to be 8.1 divided by 159.8 times 31. And so when I do that math, I get 1.6 kilojoules. So if you're wondering, what about choice D? Well, that would be for any student that forgot to convert from grams to moles. So if they had taken 8.1 and simply multiplied by 31, then they would have gotten the wrong answer. So the correct answer to question 49 is choice B. 1.6 kilojoules of thermal energy is released when 8.1 grams of gaseous bromine undergoes condensation. In question 50, it says the boiling points of two compounds are listed in the table above. Which statement best explains the observed difference in the boiling points? Now, CH3F and CH3I are both asymmetrically arranged with respect to their dipoles, so they're both going to be classified as polar molecules. That means that each substance can experience a combination of London dispersion forces and dipole-dipole forces. Remember that when you're comparing the boiling points of two substances, focus on the attractive forces between the molecules instead of the covalent bonds. So when I read choice C, it says molecules of CH3I contain stronger covalent bonds. I'm going to go ahead and eliminate choice C. Now, when I consider that CH3I has a higher boiling point, we're looking for an explanation for why the CH3I substance has stronger attractive forces between its molecules. Focusing on choice B, it says that molecules of CH3I are less polar. But that phrase, less polar, would imply weaker attractions between the polar molecules, and that's not going to explain why it would have a higher boiling point. So we can eliminate choice B. Now, with respect to choice D, it talks about how it's easier to break the attractive forces between the CH3I molecules. Again, that's not going to explain why it has a higher boiling point. So why is the correct answer to question 50 choice A? It goes back to London dispersion forces. So with London dispersion forces, that will increase the polarizability of a molecule with an increasing number of electrons and the size of the electron cloud. We're comparing fluorine with iodine. So iodine has a larger electron cloud than fluorine. That means that the CH3I molecule has a larger electron cloud. So molecules of CH3I are more polarizable and they would experience stronger London dispersion forces, the attractive forces between the molecules. So the correct answer to question 50 is choice A. In question 51, it says the curves in the figure above represent the distribution of particle speeds for two samples of gas. Which of the following choices is most likely to represent these two gas samples? So on this slide, I've got the same diagram, but different reasons why. So on the left, I say that heavier particles have a slower average speed, lighter particles have a faster average speed, so that is true. And on the right side of the slide, I'm talking about a difference in temperature. So a lower temperature is associated with a slower average speed, and a higher temperature is associated with a faster average speed. Let's use this information to analyze the four choices in question 51. So slower speeds for curve 1 according to the information in the diagram, faster speeds for curve 2. So starting with choice A, we have helium at 400 Kelvin and helium at 300 Kelvin. But 400 Kelvin is the higher temperature, and that would result in faster speeds, so we can eliminate choice A. Now, moving on to choice B, we have helium and neon at the same temperature. But according to the information on the periodic table, helium is lighter than neon. Again, that would result in faster average speeds for the lighter particles, so we can eliminate choice B. Moving on to choice C, argon is actually heavier than neon. So the correct answer to question 51 is choice C. Heavier particles would result in slower speeds. And the reason why choice D is incorrect is because argon is actually lighter than krypton. Again, that would result in faster speeds. So the correct answer to question 51 is choice C. In question 52, it says a student prepared two saturated solutions of calcium sulfate by adding excess solid calcium sulfate to distilled water and stirring until no more solid dissolves. The second solution prepared by the student had a larger final volume, as indicated by the two beakers shown in the diagram below. Which of the following choices gives the correct comparisons of solution 1 and solution 2 with respect to the value for the concentration of the calcium ion in the solution and the number of moles of calcium ions in the solution. So when I'm focusing on the fact that each solution is saturated, then each solution has the same concentration of calcium ions because that is related to the value of the KSP. So if each solution has the same concentration of calcium ions, let's go ahead and eliminate choices C and D. Now, with respect to the number of moles of calcium ions in the solution, since solution 2 has the larger volume, that means that solution 2 contains a greater number of moles of aqueous calcium ions. So the correct answer to question 52 is choice B. Now, as we take a look at question 53, we can see another example of a multiple choice question set. So questions 53 through 55 refer to the following information. It says a student is studying the reaction between propanoic acid, HC3H5O2, and sodium hydroxide, NaOH, as represented in the balanced equation above. The student uses a solution of 0.0750 molar sodium hydroxide, a burette, a pH meter, and an Erlenmeyer flask to titrate a 25 milliliter sample of propanoic acid. The student's data are shown in the following graph. So we have a titration curve. Let's look at question 53. It says the pKa value of propanoic acid is closest to, and we see 4 numerical choices. Now in topic 8.5, acid-base titrations, it says at this point, the half equivalence point, there are equal concentrations of HA and A minus, so the weak acid and the conjugate base, and so pH equals pKa at the half equivalence point in a titration. So where is the location of the equivalence point on this titration curve? Well, that would be after 12 milliliters of the sodium hydroxide is added. So what's half of 12 would be 6. So at 6 milliliters, that's the half equivalence point. And so what is the pH of the solution at the half equivalence point? It looks like it's approximately 5. So the correct answer to question 53, the pKa value of propanoic acid, is closest to 5. Now let's move on to question 54. In question 54, we have to calculate the molar concentration of the propanoic acid solution. Remember that they gave us a balanced chemical equation between propanoic acid and sodium hydroxide. There is a 1-to-1 mole ratio between the propanoic acid and the sodium hydroxide. Let's take the equivalence point, which would be after 12 milliliters of the 0.0750 molar sodium hydroxide, and if we know the volume and we know the concentration, then we can calculate the number of moles. So the volume would be 12 milliliters or 0.012 liters. The concentration of the sodium hydroxide is 0.0750 moles per liter. And again, there's that 1-to-1 mole ratio between moles of sodium hydroxide and moles of propanoic acid. So when I pick up my calculator, I will do 0.012 times 0.075. Now, when I do that math, I don't get the molarity, I get the number of moles. So if this is the number of moles, then what is the volume of the propanoic acid solution that was titrated in this experiment? Let's go back to the description of the experiment. A 25 milliliter sample of propanoic acid was used, so therefore if I take the number of moles and I divide by the volume, I will get the molarity. So I'm going to take 9 times 10 to the negative 4 moles, and I'm going to divide by 0.025 for my volume in liters. So the correct answer to question 54, what is the molar concentration of the propanoic acid solution? It is 0.036, and so the correct answer to question 54 is choice B. Now, there's one more multiple choice question in this multiple choice question set, and that is question 55. In question 55, it says, the student repeats the experiment, but uses a solution of 0.150 molar sodium hydroxide as the titrant. Which of the following graphs shows the titration curve that would be expected for experiment 2? So let's compare the concentration of sodium hydroxide for experiment 2 to the concentration of sodium hydroxide from experiment 1. In experiment 1, it was 0.0750, and now in experiment 2, it is 0.150. So how does a solution of 0.150 molar sodium hydroxide compare to the solution used in trial 1? It is twice as much. So the sodium hydroxide solution used in trial 2 has twice the concentration as the solution used in trial 1. Now, as far as the equivalence point is concerned, we had an equivalence point for trial 1 of 12 milliliters. If we use a solution of sodium hydroxide that is twice as concentrated, then we will need half the volume. So in trial 2, the equivalence point should be reached at a volume of 6 milliliters, and so therefore that means that the correct answer to question 55 would be choice D. So looking at choice D, I see an equivalence point at 6 milliliters. Well, that's the end of this 3-question multiple choice question set. Let's go ahead and move on to a brand new question with a brand new situation. This is question 56. Question 56 says the particle diagrams shown below represent the ions present in solutions of cobalt nitrate, which has the chemical formula CO and then NO3 in parentheses times 2, and potassium carbonate, which is K2CO3. When these solutions are combined, the cobalt nitrate and the potassium carbonate, a precipitate is formed. Which of the following diagrams is the best representation of the reaction mixture after the solutions are combined and the reaction goes to completion? So the first thing I will do is try to write a balanced chemical equation for this precipitation reaction. So we have cobalt nitrate reacting with potassium carbonate. The charge on the cobalt ion is +2. The charge on the nitrate ion is -1. The charge on the potassium ion is +1. And the charge on the carbonate ion is -2. So the cobalt will combine with the carbonate to produce cobalt carbonate, and the potassium will combine with the nitrate to produce potassium nitrate. Now, what I have is a balanced chemical equation, but you can see I've got question marks inside the parentheses on the right side of the equation. So I know a precipitate has formed, but at the moment, I might not be sure if the precipitate is cobalt carbonate or potassium nitrate. So one of the things that you should know for the AP Chemistry exam are these 4 ions: sodium, potassium, ammonium, and nitrate. So all salts or ionic compounds that contain one of these 4 ions are classified as soluble according to the AP Chemistry curriculum. So one way to remember the 4 soluble ions is to think of them with the acronym SNAP or SNAP. Sodium, nitrate, ammonium, and potassium, when they are present in ionic compounds or salts, then they will be soluble. So what is the identity of the precipitate? If potassium nitrate is soluble because of those soluble SNAP ions, I will put an AQ next to the potassium nitrate. That forces the other substance, the cobalt carbonate, to be the identity of the solid precipitate. Now let's take a look at the 4 particle diagrams. So the identity of the precipitate is the cobalt carbonate. So right away I can tell that choices C and D are incorrect, because at the bottom of the beaker it's showing a collection of solid as solid potassium nitrate. So we know that choices C and D are incorrect. Now when I look at choice A, there is a problem with that particle diagram. It shows 3 carbonate ions and 2 cobalt ions, so we don't have charge balance. And in the aqueous portion of the particle diagram for choice A, I see 6 positive potassium ions, but only 4 negative nitrate ions. So the reason why choice A is incorrect is because there's no charge balance for either the aqueous portion or the formation of that solid precipitate. So the correct answer to question 56 with the correct identity of the cobalt carbonate precipitate and correct charge balance in the particle diagram is choice B. In question 57, it says, considering the value of the equilibrium constant K for the reaction represented by the equation above, which of the following must be true for the standard cell potential and the standard Gibbs free energy change for the forward reaction? So the value of the equilibrium constant K is very large. So from topic 9.5, free energy and equilibrium, the phrase thermodynamically favored means that delta G is negative, and the products are favored at equilibrium under standard conditions where K is greater than 1. And for topic 9.9, cell potential and free energy, a thermodynamically favored reaction results in a positive cell potential. So this is what we know. If K is greater than 1 at standard conditions, the forward reaction is thermodynamically favored, the sign of delta G is negative, and the sign of the cell potential is positive. So the correct answer to question 57 is choice C. In question 58, it says a 71-gram sample of aluminum, initially at 22 degrees Celsius, absorbs 6.24 kilojoules of heat. The final temperature of the aluminum is closest to which of the following? Assume the specific heat capacity of the aluminum is constant at 0.896 joules per gram degree Celsius. So we're going to use the equation Q, the thermal energy or the heat, is equal to M, the mass, times C, the specific heat capacity, times delta T, the change in temperature. So I have the M, which is the mass of the sample, and that's 71 grams. I have the C, the specific heat capacity of aluminum, which is 0.896 joules per gram degree Celsius, and my delta T is, well, we don't know. That's what we're trying to find. Now, it says 6.24, but watch out because these units are kilojoules, not joules. So I need to multiply that value by 1,000 to convert from kilojoules to joules. So it's not 6.24, it's actually 6,240 joules. Now I'm going to solve for delta T. So I will divide both sides of the equation by the product of 71 and 0.896. So this is my setup. I will pick up my calculator and I will do 6,240 joules divided by the product of 71 grams and 0.896 joules per gram degree Celsius. So my units of delta T are degrees Celsius. Now, 98.1 is what I got on my calculator. But again, watch out, this is not the final answer. I'm going to go ahead and eliminate choice C, but some students might have picked choice C, that is the delta T, that is not the final temperature of the aluminum. So if the initial temperature of the aluminum is 22 degrees Celsius and the change in temperature is 98.1, then we're going to take 22 plus 98.1 to get our final temperature. So 22 plus 98.1 gives us 120.1 degrees Celsius. So the correct answer to question 58 is choice D. In question 59, it says, which of the following elements has the largest first ionization energy? So based on our knowledge of periodic trends for ionization energy increases from left to right across a period, and ionization energy decreases from top to bottom down a group. And these are the 4 elements that we have to consider. So looking at our periodic trends, then that would make strontium the highest value for first ionization energy. So the correct answer to question 59 is choice B. Okay, last question, almost done. This is question 60. It says an incomplete mass spectrum for rubidium is shown in the diagram below. Now, rubidium has two natural isotopes. The percent abundance of rubidium-85 is 72%. Which of the following diagrams is most likely to represent the mass spectrum of rubidium? So when I look on the periodic table and I find that the average atomic mass of rubidium is 85.47, so I will use that information. And I know that since one isotope has a percent abundance of 72%, that means that the other isotope has a percent abundance of 100 minus 72, or 28%. Now, what I will do is I will set up an algebraic equation and see if I can solve for the mass number of the other isotope of rubidium. So 85.47, which is the average atomic mass, and that is equal to the mass number 85 times its percent abundance as a decimal, so 0.72, plus the other mass number, which I don't know yet, times its percent abundance as a decimal, which is 0.28. All I have to do is the algebra to solve for x. So I will go ahead and multiply 85 by 0.72, and that works out to be 61.2. Then I will subtract 61.2 from both sides of the equation, and I get 24.27, and that is equal to 0.28 times x. Now I will divide both sides of the equation by 0.28, and what I get is that the mass number of the other isotope of rubidium, that works out to be 87. So we're looking for a mass spectrum that shows two isotopes, 85 and 87. So that makes the correct answer to question 60, choice C. All right, well done, you did it. This is the end of the video. I hope that you found all of these answers and explanations helpful, and that you can use this practice exam as good preparation for the multiple choice section on the AP Chemistry exam. So this is the end of the video. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.